All right, so at any rate. Okay, so last time we were together, we started doing the strong interactions, and hopefully you could see how much more complicated calculations were due to all of this color stuff. However, remember that we kind of extracted from it basically the results of QED along with the color factor results. And the color factor results are what we're going to continue keep talking about today. Today is actually not going to be a lot of equations. It's more just going to be ideas tossed around because I don't want to get too deep into the calculations. But first and foremost, recall that last time what we demonstrated was that, let's see, yeah, 4/3, okay. If we use the colorless combination, which is of course state 9, which you just add on your quiz, okay, for a meson, where hopefully if you look at this little bluish sheet I gave you, you'll start realizing the spectrum of hadrons, which is mesons and baryons. Mesons are quarks and antiquarks. Baryons are 3 quarks or 3 antiquarks. But anyway, we were talking about mesons, which are these 2 quark states, and they always have to have a quark and an antiquark. And what we found was that if our quark and antiquark were in this combination of their color assignments, then the color factor, which is this factor F, which basically dictates how this interaction would compare with an electromagnetic interaction. We'd already found the electromagnetic interaction was positive, so if the color factor was also positive, then the net result would be an attractive force. And if the color factor turned out to be negative, it would change the attractive QED force into a repulsive QED force. And only for this combination does it turn out to be positive. In this case, it actually turned out to be 4/3 for the reaction that we were considering. Okay? That's just a very quick review of what we did for mesons. All right? So again, we just considered, you know, a meson diagram like so, where maybe we had a red coming in and we did a blue. This was a colorful version. This is not the colorless state here, but we did the colorful version of this, and then we found that F was -1/6. So the M was basically the M for QED times F. And the M for QED, these would be attractive because one of these is positively charged, one is negatively charged, so that's obviously attractive under electrodynamics. So the F from the color calculation, part of the calculation, determines whether this remains attractive or whether it turns repulsive. For this combination, we had F negative, so this meant it's repulsive. Only for this combination is F positive, so only for this combination was it attractive. Okay? Now I'll talk about what the importance of only this being attractive is in a few minutes, but what we should now do is we should consider another set of processes, because after all, we say quarks are found not just in meson states, but also in baryons. Yes?
Why does the sign of M matter if in Fermi's golden rule we take M squared?
Don't worry about that right now. Don't worry about that right now. I'll get back to that later. Okay? But now what I want to do is I want to consider an example of baryons, baryons. So for baryons, again, we're considering now 3 quarks, which I'll label Q1, Q2, Q3. You could also do an anti-baryon, in which case it would be 3 antiquarks, but they all have to be either quarks or antiquarks. You can't mix them, okay? So we're going to think of a baryon as a combination of 3 quarks. And what we want to do is we want to show that all forces are attractive if it's in a singlet state. Okay? Now you might wonder, what do you mean all forces, and then what is the singlet in this case? We know what the singlet is in this case, it's given right there, but what's the singlet look like if you have 3 quarks? So I'll illustrate illustrate all this. But this is basically what we want to demonstrate, all right? And this is going to lead to that conclusion that in some ways, baryons and mesons have to be colorless, all right? So here we go. So here's our, we're going to do an interaction much like we did for the mesons. We're going to have these 3 quarks coming in, and the same 3 quarks going out. Okay? And, well, this story, if you think about it, could be quite a bit more challenging than the meson case. Because for the meson case, we basically had 2 quarks. And if F was plus, they were attractive. If it was minus, they were repulsive. Here, though, depending on how we fill this in, we could consider the forces between this quark and this quark, or this quark and this quark, this quark and this quark, this quark, this quark, this quark, this quark, this quark, this quark. We could actually pair these up in different ways and ask whether they're repulsive or attractive. What's worrisome is that in many situations, some of the forces are attractive, but some of them are repulsive. Okay? So you might have these two exerting an attractive force on each other, but maybe this is repelling this and this is repelling this. So the question then is, would it stay together as a bound state? The only definitive answer we can give is if the force between any 2 quarks is attractive, then it's definitely potentially a bound state because everything is attracting everything else. If any of the forces are repulsive, you can't guarantee that it's a bound state. Okay? So that's the way we're going to approach this. So first and foremost, we can start by just considering 2 of the quarks. Okay? And this story is going to play out differently than the story we did last time, because last time we did a quark and an anti-quark. This is a quark and a quark, so it's going to play out a little bit differently. So let's start with a quark and a quark go to school together by exchanging a gluon. So we've got a Q coming in, we've got a Q leaving, and it doesn't matter what quark you pick. It could be the up quark, the down quark. That's not important. The only thing that those things will change are the masses, up, down, strange, strom, top, bottom. They all have different masses, but the masses are just going to be variables in here, so don't worry about it. What's important, though, is the color assignment. Okay? So we're going to have a Q coming in here and a Q leaving here. Notice this is Q and Q. These are matter particles, not antimatter particles, because all of the ones here are matter and all the ones here are matter. So I'm thinking about the interaction between a pair of these. That's what this diagram is giving. Okay? Let me go ahead and assign my momenta. That's 4 and that's 3. Sorry, I was just randomly labeling things, but these are the momenta labels. And in this case, if I write down the M expression, I'll get minus GS squared over 4 I over Q squared times U bar 3 gamma mu U1 U bar 4 gamma mu U2 times the color factor, which is C3 dagger lambda alpha C1 C4 dagger lambda alpha C2. Okay? We good? Now, this is a quark and this is a quark. So these are going to have the same charge. So this quantity right here, besides the color factor, is going to represent repulsive QED result. Okay, so this part of the answer for M is basically the same thing you get if you were doing QED. However, since these have the same charges, it's a repulsive term, okay? So now, if the color term comes out to be positive, then this entire thing will be repulsive. If it comes out to be negative, then this will be attractive, okay? All right, so we need to evaluate the color combination assignments for the C1, C3, C2, C4. And we did this last time. Well, this isn't going to quite play out like it did last time, strangely enough, okay? So remember last time we had what was essentially a color assignment for a quark and then a color assignment for an anti-quark. So we might have called that C bar prime. The prime is just because it might be a different quark than what you're sending in. So we have maybe an up and an anti-down or something like that. But anyway, we might wonder, what were the possible combinations of the color and the anti-color? And it turns out that mathematically what you would say is that you've got 3 choices for C, and then you have 3 bar choices for C bar, okay? And the spectrum of this is actually, if you're combining these two, it's a direct product, but you can actually decompose that into what we called an octet plus a singlet. Okay, so this is taking a product representation and representing it as the sum of ordinary representations. All right? And of course, we discovered in this story that the singlet, which is this state 9, that's the only color choice that we can make where it's always attractive. The octet is a set of 8 states where the transformations take you from one of these to the other. Those are not invariant, they're not singlets, they're just transformations between those 8. That's what we call an octet. Versus a singlet, singlet's just invariant. Okay, that's an observation about the group property. Okay, what was important though is that we did the calculation and found that F was positive for this one and it was negative for all of these. Okay, well now we are not considering C bar prime, but rather we're considering C prime. And it turns out in this case, we are once again choosing 3 possible colors for the first one, but we're also choosing 3 possible colors for the second one. Okay? Now one way you can think about this, and I'm not going to dig too deep into the details, remember that if you're doing a U transformation, the U on this is different than the way U acts on this, okay? However, here, the U transformations on either of these are the same because these are the same representations. They're both these 3 component vectors. So now we want to combine 2 3-component color vectors, and it turns out when we decompose this, what we end up getting is 3 plus 6. In both cases, they add to 9, which is what you would expect. So this guy is a triplet, and this guy is a sextet. How many of you have heard the word sextet? Sexy, right? Yeah. Glad you guys laughed. That was my joke for the day. Hope you have better ones. Okay.
No, I think we're peaked now.
Huh?
I think we've peaked with that joke.
Okay, fine. All right, now I actually wrote down what the octet states look like for this case and what the singlet state looks like. The singlet state's right there. You might be wondering what the triplet and the sextet look like, and I'll just give you these very quickly. The triplets look like the following. 1 over root 2 RB minus BR. Notice there's no bars over the colors because these are the colors of real particles, not antiparticles. 1 over root 2 GR minus RG. And 1 over root 2 Davis.
Blue, green minus green, blue.
Exactly. Good guess. Okay, so these are the triplets. Notice there are 3 of them. Okay. And then we have the sextet. And I'll just very quickly write this down. We got RR, blue, blue, green, green. 1 over root 2, R blue plus BR. 1 over root 2, GR plus RG. 1 over root 2, what is it?
BG plus G.
Yeah, it's, well, GB plus BG doesn't matter, GB plus BG. Okay, this is the sextet. Now what? Does anyone notice a particular symmetry or anti-symmetry that these share?
The sextets are symmetric, the triplets are antisymmetric.
Exactly. These are anti-symmetric under the exchange of color with color prime. If I interchange RB, this becomes BR, this becomes RB, so this is minus what I started with. That's what anti-symmetric means. Okay? Whereas these are symmetric. Okay? Now, in case this looks weird to you, I think you might have seen this in quantum mechanics, but now I'm highly doubting anything that I think you saw in quantum mechanics you actually saw in quantum mechanics. So I'll just point this out to you and you can be like, oh. but just in case, if you're doing a spin, a half in 3D, then what we're talking about is that if I take 2 spinners, which each have a 2-dimensional representation, and in 3 dimensions, the spinner has 2 components, so it's a 2-dimensional representation. If I take 2 spinners and I put them together, and I want to, basically add their spin, then the total can come out to be either a scalar, which is spin 0, or, and this should be a plus, or a vector. Is anybody familiar with that result? If I take 2 spinners, like 2 electrons, okay, and I just back the hell up, so far that they just look like a single particle, then the question is, if I can no longer distinguish those as individual particles, and I just see it as one blob of a particle, what spin can that blob of a particle have? Well, it depends on how these are aligned, but the answer is that if they're anti-aligned, it'll be 0, which is a scalar, and if they're aligned, it'll be a vector, okay? But does that make sense? I'm basically saying I have 2 objects they're both spin a half, but I'm looking at them so far away that they just look like a single object, which has a single spin, and it's either a scalar or a vector. That's what we're doing here too. We're taking 2 quarks, and we're asking, if I just step back, what is the possible total? It's actually the color configuration, and it can either be a triplet or a sextet, all right? Now, well, it turns out, and I'm not going to go through this calculation again because we went through it last time and it was a pain and I don't want to go through it again, but the F factor for triplets is minus 2/3, and the F factor for sextet is 1/3. Okay? As we talked about, this is repulsive. So for the states that are in the triplet is the overall M for the QCD effect, is the overall M attractive or repulsive? Don't make me, damn. Henry.
Sorry, repeat the question.
So this part of the M is representing a repulsive interaction. For the triplet states where F is negative, is the overall interaction attractive or repulsive? It'd be attractive. Okay, so this leads to attractive interaction. And then for the states in the sextet, this lets it remain repulsive. Okay? Now, okay, that's the story for 2 quarks. Now we should talk about the story for 3 quarks, because a baryon has 3 quarks in it. Well, I'm not going to go through the calculation, but rather I'm just going to show you how the symmetry breaks down. So in the case of a baryon, we have 3 cross 3 cross 3. We have 3 baryons, and each of them have 3 color states. This decomposes, if I want to step back and look at this thing and ask, okay, I got 3 quarks there, but I just want to view it as a single particle. What could its color states be? Turns out they can be either a 10, or an 8, or another 8, or a 1. Folks, just give yourself a moment to realize that 3 times 3 times 3 is 10 plus 8 plus 8 is. You realize these numbers are all combining accurately. I just want to point that out. That's like one of the first things, like, yeah, this times this has got to be this plus this, and the numbers have to work. It's like that simple. Okay, so I mean, I could give you a question on a quiz where I like leave off the 1, and I can say, is this accurate? And you could go, hell no. Honestly, like, that's sometimes. Okay, so first of all, these are totally symmetric decouplets. So we call it a 10-component object. For example, we can have 1 over root 6 RGB plus BGR plus RBG. I think it said RBG, but it's RGB plus BGR plus RBG. Oh, shoot, plus BRG plus GRB plus GBR. It's totally symmetric though, because if I interchange any 2 of the colors, I'll end up with the same expression. But you have to have this many terms because you're going to allow the interchange of any 2 of the 3 colors. Okay? But we can actually do easier than that because we can do, oh, hold on, yeah. Oh, we can also do RRR. No, don't trust me on that. Yeah, no, don't trust me on RRR. Don't trust me on that. But anyway, yeah, I'm a little bit. No. So,
Is it, or is there like a separate symmetric?
no, what I'm, yeah, hold on. Isn't it? Oh, yeah, never mind. Yeah, so it's the same as what I had up here. So this is symmetric under C goes to C prime, because this, if I just interchange R with green, this will become green, but then this will become RR. Okay, so it's all of them together that you get the symmetry for. So other terms will be RRR, etc. And then this entire set, okay, if I do an interchange of any 2 colors, every one of these will either transform to a different one, but this one in particular will stay itself. Okay. Sorry about that. So that's the 10. The 8s are mixed symmetries. Octets. Obviously they're octets because they have 8 components. So for example, here we have 1 over root 2 RB minus BRB, 1 over root 2 G RB minus BR, etc. Okay? Don't worry about these. The 1 is the most important one. 1 is totally antisymmetric. Okay, and we can write this one down, and it's only one of them, 1 over root 6, RGB minus RDG minus GRB plus BRG plus GBR minus BGR. Okay? That's the one that's most important. Why? Because it turns out, and again, I'm skipping a huge amount of calculation here just to get to the answer. It turns out that only if our 3 quarks in a baryon are in this singlet state, only in that case is the interaction between any pair of the quarks attractive. And that is something which we know could lead to a bound state because you have 3 quarks and they're all interacting in an attractive manner. For anything in the decouplet or the octets, some of the interactions will be attractive, but some of them will be repulsive, so it's hard to say. Okay? Now, so, the moral of this story, are there any questions about this before I erase all this, because we're not going to use it?
For the 3 quarks, is the QED still repulsive in the F?
So,
The sign of
yeah. Okay, so, now I'm going to get all wordy on you. Skip all these things. Somebody leave? Huh? Oh, yeah. Okay. All right. So the moral of the story is that for bound states of quarks, whether they are mesons or baryons, it doesn't matter. The color configuration should be the colorless singlet. Okay? So it's true for the mesons, it's true for the baryons. You have to have a colorless state in order for that to be the bound state of either a quark and an antiquark with 3 quarks. Now, on the other hand, SU3 as our gauge symmetry allows only colorful octet gluons. So the gluons cannot be in the colorless 9th state. Rather, they have to be in the octet. It's a pair. You can think of a gluon as a pair of colors, color, anticolor. And they have to be in one of those 8 octet states that we talked about last time. Okay? So matter has to be colorless, whereas gluons, the force particles in SU3, or the QCD interactions, the force particles have to be colorful. Okay? That's the end of this. Now let's actually compare this to what we see in an experiment. In an experiment A, we never see free quarks. And B, we never see free gluons. Okay? So it turns out you can slam things together as hard as you want. You can never break a meson up into a quark and an anti-quark separate. You can never do an experiment where a gluon comes out. Gluons will always play these virtual roles, largely. Okay. Why is that the case? Well, it turns out the answer to that is rather challenging. In fact, it's never been fully proven. But what we have is what is called the color confinement hypothesis. And that is any free or long-lived state in QCD must be a color singlet. This immediately implies both of these. Because if anything that you can see as an existing particle or an existing thing must be a color singlet, you can't see an individual quark. The only way we could get color singlets was to either combine them into mesons with a quark and an antiquark and then give them that particular singlet configuration of their color assignment. Or we could combine 3 quarks or 3 antiquarks into a baryon and then give them that appropriate singlet color assignment. That's the only way we can get the quarks to be colorless, is with those combinations. Furthermore, gluons have color. They're part of those 8 states that are colorful. But the only thing you can see is colorless stuff, so you can't see gluons. Okay? Now, that's it. Right? All I have to do is prove it. Does that make sense? You know what this is your homework problem? Well, what's good is if you do this as your homework problem, you should go ahead and buy a ticket to Norway.
Well, Sweden is right now.
Oh, sorry, Sweden. I meant Sweden. Yeah. Okay. Why can't we just prove this? Why can't we prove this? Well, what we'll study in due time is renormalization. And what renormalization will teach us is that for QCD, the coupling in the fundamental cases, G, can be greater than 1. All right? If the coupling in QCD is greater than 1, what epically fails?
Only taking the lower order Feynman diagrams?
Yep. Remember, when we do Feynman diagrams, we start out with tree level, and then we just go higher and higher, but this has a factor of G squared, this has a factor of G squared, blah, 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 blah. Keeping the lower order diagrams to get the answer depends critically on G being less than 1. For QCD, it can be greater than 1. So you cannot rely on the Feynman calculus to give you the answer. I mean, you can rely on it if you calculate every single term in the series. Yes?
How would there be a finite number of terms?
How would there be a finite?
Yeah,
There's
number.
not. There's always an infinite number.
Okay.
That's why I got plus dot, dot, dot. Yeah, there's an infinite number. So there are situations in QCD where this Feynman approach of an approximate answer, it just doesn't apply. Okay? Now, there are approaches where you can actually get answers. So for example, lattice QCD. This is not at all using Feynman diagrams. Rather, this is taking space-time and replacing it with a lattice of points. And then on each point, you give it these degrees of freedom. Basically, you're taking a field which is defined over the continuum of space-time and you're restricting it to values at points of a lattice. And in that situation, you can do calculations without this approximation technique. Okay? Where this gets really tricky is taking the limit that the spacing goes to 0. That gives you a lot of really weird effects which still haven't been completely panned out. But this is an avenue of high energy research which is still ongoing. When I was a grad student at CU actually, our high energy theory program had 4 faculty. We had a phenomenologist who was like, anyway, he's a theorist. We had a string theorist, and then we had 2 lattice gauge theorists. Okay? So this is an open field, you know, in high energy theory if you think you might be interested. Very calculational intensive, computer calculational intensive. However, it turns out that string theory gives us a lot of other things which we can actually throw at this problem. For example, supersymmetry and dualities. Okay, I won't go into detail on this, but supersymmetry is a means of sometimes calculating the exact answer to a problem, even though you can't calculate to all orders of magnitude in the Feynman approximation. And then dualities are actually interesting because dualities, one of the interesting features of dualities is that you can take a theory which has G greater than 1, and you can totally substitute it out with another theory with a coupling less than 1. And those 2 theories end up being equivalent. But I won't go into any more details on that right now. I might talk about it next Thursday. Okay? But what I want to do now is I actually want to take this color hypothesis that everything in the strong interactions has to exist in colorless states, and now I want to go back to another question which I posed last time, and now we're finally going to get to answer. Okay. So let's consider why QCD interactions seem weak. I mean, what's the most prevalent force that you experience of the standard model forces? QED, yeah. I mean, if I take my fingers and I push them together, what's the force which is keeping my fingers from going into each other? It's QED. It's not this QCD nuclear force. So why is it that even though QCD is the strongest of the interactions, I mean, I should stress that the coupling for the strong interactions is larger than the coupling for the weak interactions, which is larger than the coupling for electromagnetism. This is just the factor of G that you put in for each vertex in a Feynman diagram. These G's are related to the alphas, so if the alpha stronger is greater than alpha E, GS is greater. So you can do this. Okay? But at any rate, the strong interactions, their vertices are more strongly coupled than the electromagnetic vertices, yet electromagnetism seems to play a bigger role. Why is that the case? Okay? Well, let's consider a particular process. Let's consider, now first of all, we should think about mesons or baryons, because that's, in terms of the color part of the story, you've got to be dealing with quarks for the strong interactions, and we got to think about a baryon or a meson. So I'll think about a baryon, because this is obviously one of the more prevalent cases. But by the way, so up, down, quark, that combination is the proton. And that happens to be the lightest of the baryons. So it turns out that this, in principle, cannot decay. I mean, how would this decay? There's no route by which this could decay, okay? A neutron is up, down, down. The down quark is heavier than the up quark, so this thing has a larger mass than this, and this decays through the down quark, turning into an up quark, and then you get another particle coming off of that, okay? Now, where was I going with that? I forgot where I was going with that. Oh, okay. Anyway, the proton is basically a down, an up, and an up. So we're gonna have three lines coming into our Feynman diagram. And then all we're gonna do is we're gonna have a proton scattering with another proton. I'll do up, up, down. And so we'll have these come in like this. And then we just want a proton coming out. Whoops. Okay, so I'm going to have this, 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 this. And now the simplest way to complete this diagram is as follows. Are you ready? These are just coming along for the ride. This is going to exchange a gluon with that. That's the simplest diagram you can imagine, right? Yes?
Is there a rule, I'm sorry, this is dumb. Is there a rule against just connecting all of them horizontally? I mean, that wouldn't be an
Well, that's not an interaction.
Okay.
Yeah. Okay. All right, so that's the simplest diagram I could imagine. Right now, now remember, if I'm doing a QED diagram, I have a proton, a proton, a proton, a proton, and they exchange a photon. And notice this is second order, so this is going to be about alpha strong squared. This is second order in the number of vertices, so this is going to be order alpha E squared. Well, alpha strong is bigger than alpha E, so you would think you'd have something like that, or maybe just bigger. Not necessarily a lot bigger. Okay, that seems like the way it should play out, right? Well, there's two problems to this story and the resolution to it. You'll be like, oh, I get it. First of all, the protons must be in overall color singlets. So what that basically means is that the protons should be overall colorless. So I'm asking for a colorless proton to interact with another colorless proton. The fact that there's color is if you look at a quark and a quark and a quark and a quark, okay? So there's a sense in which this interaction is sort of like the van der Waals interaction in chemistry. You know, you can have two neutral atoms interact with each other because they're not completely zero charge, they're a charge distribution, and then the charge distributions can interact with each other. But look, if I take a positive and a negative charge, that direct interaction is way stronger than the van der Waals, because the van der Waals is just sticking to the fact that this is got, you know, some sort of polarization, okay? Also, this is quite interesting, protons, these are not virtual particles. Protons are like real things. You can hold on to them in your hands. I say that because earlier I was doing quark diagrams, you know, with quarks, and these quarks, you can't take them and separate. You can't do that. You've got to keep the quarks together. But protons can exist, you know, for as long as you want. You can pull them as far apart as you want. But here's the thing. If you take these two protons and you separate them, the thing that's being exchanged between them must exist almost approximately as a real particle. It's true that it's virtual, but if the separation between the protons is really far, the particle they're exchanging must approximately become a real particle as opposed to a virtual particle. That's a limit that you can take. So essentially, this picture is not accurate. All right? We have to improve it. So let's do that. With color. Draw me a little colorful picture. So here we go. Whew. So once again, we're going to start out with a proton, up, up, down, and it's going to scatter into another proton, which again is going to be up, up, down. And we're going to take a proton, which is down, up, up, and it's going to go into another proton, which is down, up, up. Yes, okay, so here we go. Oh my God, this is complicated. Okay. So we're gonna have this guy come in with blue color. So we should do this. And it's gonna hit an intersection, and it's going to be changed by the gluon in question to a quark, an up quark of red color. Because remember, what do gluons do? So what is the gluon that is emitted from this moving down? What is its color assignments? We have blue coming in and red going out, so it's anti-blue red, okay? So I might do this. I didn't do it like this, but I might do this, where this is anti-blue and red gluon, okay? Now, and wow, I did this in the craziest way. This is so weird. Anyway, all right, so I might just let that be inferred. Now we're going to have this guy come in, and we're going to have him transition to a blue. Okay, once again with the gluon. Okay, which is going to be anti-green blue. And then we can have this guy come in, get that guy, and then we'll have him transition to blue. Yeah, I know. Well, remember you can do the gluon either way. You can either have it going up or down. If you have it going down, it's carrying away the blue, okay, and it gave up red. But that same gluon down here can cancel this red and then give you back the blue. Does this make sense? Okay? I'm just going to draw a lot of these, so just get used to it. Okay, so now our green can pop out of here. And once again, this can carry blue up. Okay? So I'm going to get my arrows to work out. So notice we have this gluon going down is blue and anti-red. Here it imparts blue and takes away the red. Okay. This gluon going down is green and anti-blue. Here it's giving anti-blue and green. You following? So let me finish the diagram. Oh my God, this is such a sorry. Okay, so this is going to come down here. Okay, that's again the blue-green. It's a real headache. All right. Bam! Okay, all I want you to realize is that if you track the color changes that all of these gluons are carrying, they're in agreement. Like this is an incoming blue, outgoing green. That gluon is born, and then it dies with an incoming green and an outgoing blue. Similarly, we have red, blue. Oh, wait a minute. That's not a particle. That's not a gluon. That's a quark. Anybody notice that? The two things that constitute what is overall the exchange between the two protons, those are quarks. Well, that combination of quarks has a name. It's called pi zero, pion. Okay? So, well, here we go, folks. The interaction of two protons via the strong interactions, if you stand back and ignore the fact that these are actually made of quarks and just say I got a proton and a proton interacting via the strong interactions, protons obviously interact via electromagnetism, but they also interact via strong interactions. They interact via the exchange of a pion. But a pion is a meson. Notice color, anticolor. This thing is colorless. As I said, everything in the QCD interactions needs to be. This can be long-lived, because once again, I could take two protons which are well separated. Whatever they're exchanging could actually approximately be real. Well, this is certainly real. And it's allowed, it's colorless. So that solves that colorless problem. Well, remember this little argument? If this is the lowest order diagram, what order of alpha S does it take? 8. To get this diagram, I need 8 indices. So even though alpha S is larger than alpha E, alpha S to the 8 is less than alpha E squared. Because the electromagnetic interaction between two protons is still given by this diagram. Okay? So this is a much more complicated scenario. But at least we see an explanation for why strong interactions are overwhelmed by electromagnetic interactions. Because the strong interactions don't even kick in until you're at these higher order diagrams. And that's because of this colorless thing. Notice the blue, green, red, that you might think of that as colorful, but actually the combination of all three colors constitutes colorless. But just what's important is this is colorless, this is colorless, this is colorless, this is colorless. That's one of the ways you extract this diagram. If you did the interaction between a proton and a neutron, this contribution would be 0 because a neutron is chargeless. This would be the same. So for the interaction between protons and neutrons, this is the key ingredient versus electromagnetism. If you're talking about two protons, this is way more important than this. So this does play an important role. It's not that big of a deal when you're talking about protons and protons. Okay? Now, hopefully this picture made sense. It's not true. Sorry. We'll take it for a good representation, but do you remember what the actual color assignments for 3 quarks has to be? It has to be that totally antisymmetric singlet with 6 terms. So you can't just say this quark is blue, this quark is green, this quark is red. They rather have to be in that sextet. Okay, but don't worry about that. Or that singlet, sorry, that singlet. Don't worry about it. This picture is plenty convincing. We'll just leave it at that. Okay? At any rate, I just wanted to give you an idea. This is what nuclear physics looks like. It looks like the proton is interacting with another proton through the QCD interaction, not by the overall exchange of gluons, which are the force particles, but rather by the exchange of matter particles. Pions are matter. They're mesons. They're matter. And it's exchanging of a particle. But the gluons are obviously playing a role in this. Okay? And I just say this because if you were to become a nuclear physicist, the idea of doing your calculations based on this being a photon, a gluon, or a weak boson, forget it. You'll do calculations more like this, and there's a bunch of these particles that you could be exchanging. Okay, so now I'm going to end with something which it'll just take a couple minutes, but it actually turns out to be incredibly appropriate. And that is the suggestion some time ago, prior to QCD, of why we can't see free quarks. Okay? So quarks were sort of established as what protons were made of, what neutrons were made of, but we really didn't have, before we finalized the form of QCD that we now have, before that, we really didn't have a really good explanation for why you could not get free quarks. Okay? Well, there was an idea that was put forth, and it said maybe the force between quarks was squeezed into a tube connecting them. So let me give you an example. So in QED, we might say, okay, I've got Q1, I've got Q2, and one of the ways that I can kind of imagine the force is just like by drawing the electromagnetic field diagram. So we might have something like this, but then this will also go here. Hopefully these look familiar. Okay, that's just a field diagram for two opposite charges. However, in QCD, what we suppose is that maybe instead of the field lines getting sent out, and the fields are directly analogous to photons, so this is where you could imagine these are photon lines. But anyway, maybe in the interaction between two quarks, the field lines can't escape to infinity. Maybe they are confined to starting and ending on the two quarks. Maybe they buck out a long way, but they always start and end on the two quarks. Okay? The reason this is nice is because it is exactly the fact that the electric fields generated by charged particles spread out everywhere that gives you the opportunity to separate charged particles. The fields diminish as you move away. However, if your fields are restricted to lying between these two, if you pull these apart, these fields are going to essentially exhibit a tension, and the tension force is only going to grow as you pull them further apart. So this was a proposal, before we understood QCD, this was a proposal for how we might explain that you can't see individual quarks. They always have to exist in pairs or triplets or whatever, okay? Now, these, what we might call color flux tubes, these color flux tubes, they might actually exist. But when this was first proposed, we realized that we can kind of analyze the dynamics of these. We could say, okay, I'm going to have two quarks, and I'm basically going to consider all of this stuff in a tube form, connecting them. Okay? And thinking about the dynamics of that tube was an important question. And it turned out that in studying these flux tubes, and the length of these is on the order of 15 meters. Jesus. Wow, it's not my day. 10 to the minus 15 meters. That's the nuclear length. Okay? So two quarks, you'd expect them to be separated by about the nuclear scale, just 10 to the minus 15 meters. They started analyzing the dynamics of these tubes. Again, this is before QCD was born and solved the problem. They started examining these flux tubes. And they could talk about, the dynamics of them. But unfortunately, what they found was some problems. First of all, there were tachyons.
That's tacky.
Yeah. These Fleck tubes could actually indicate that you have a state of negative, of mass squared is negative, which is like tachyonic kind of sus. It also gives you spin 2 excitations, which there are no spin 2 excitations in the standard model, right? Everything is either a scalar, that's all the matter, or it's a vector, those are the force particles, or it's a spinner. Or shoot, I'm not in it today. It's a scalar, it's the Higgs boson, it's a spinner if it's matter, and it's a vector particle, spin 1 particle, if it's a force particle. If you do this story, you end up with spin 2 excitations. There's none of those in the standard model, okay? And there are other problems, which we won't go into, all right? Well, this kind of forced most people to abandon this idea. This is stupid. You can't have tachyons, you can't have things traveling fast speed of light, spin 2 excitations we don't have in the standard model. This is obviously not a good explanation for the strong interactions. And then they found QCD, which explained all this shit, and you're like, good. Okay, because we explained it today, okay? So, but there were a couple of guys, a couple of them, who said, no, I really like this. This is pretty cool. But what they did was they said, this isn't going to be the length between 2 quarks, that's the nuclear scale. Rather, what we're going to do is we're going to drop this to 10 to the minus 35 meters, okay? Because if you drop this to 10 to the minus 35 meters, something kind of interesting happens. This spin 2 particle is small enough in terms of being this like little tube to be interpreted as a graviton. That is the force particle for gravity, which is not in the standard model. We don't do gravity in the standard model. So they found that taking this little model and dropping the length down to there gave them the opportunity to interpret this as a graviton. Moreover, if they wrote it in a supersymmetric format, which we'll talk about in due time, then the tachyons went away. Does anybody know what the hell this theory is? It's string theory. This is how string theory was accidentally discovered. They were trying to explain the strong interactions through this tube method. Turns out it didn't work. QCD solved that problem. But they continued studying it, literally 2 guys did. They continued studying it and said, well, let's take this spin 2 and make it a graviton. We'll drop the scale to this length, and we can get rid of all the tachyons by appending supersymmetry to the theory. And this was born superstring theory, which I like, and you'll hear more about next Thursday.